All right, let's continue reviewing. We didn't get very far in our last review. The quiz took a good portion of the hour. We're going to look at the quizzes tomorrow because tomorrow is going to be our math review day. Not a lot of math to know, but if you want to jot some things down, networks will be on the exam. Networks will be on the exam. Of course, that's going to be the biggest points as far as the math goes because that's the most recent. There was a little bit of other stuff. Resistance in a wire was in this last chapter as well. That's not been tested yet, so that'll be on the exam. Also, the lenses and mirrors and stuff was in this most recent quarter. So lenses and mirrors and things like that will be on the exam also. There will be no math problems from third quarter previous. So all the math will be from this quarter. Really, the first 3 quarters have already tested you on that math. That'll all just be terms. Math will come again from this quarter. Lenses, mirrors, circuits, networks, things of that nature. As far as the math, that's all for tomorrow. So tomorrow we'll look at the quizzes and do that math review. Let's continue with terms. We reviewed chapters 1 and 2. We just started reviewing chapter 3, important terms to know. I believe the last thing I asked about was force, which force is any push or pull on an object. We said that for a liquid, force is always exerted in what direction? Perpendicular or normal to any surface. What's the term that describes force per unit area? Force per unit area. Pressure. What's our unit, our typical unit for pressure? SI unit for pressure?
Pascal.
Pascals. And we said for atmospheric pressure, we can also have ATMs. We said we can also have torr. But typically pressure is measured in pascals. Force typically measured in newtons. We said the primary factor that affects liquid pressure is depth. Depth is the primary factor that affects liquid pressure. Scientists had a principle that said that if you have a confined liquid, like a water balloon, where the liquid can't escape or go anywhere else, if you apply force to one area, one surface, that pressure will transmit equally in all directions. Pressure in a confined liquid transmitted equally in all directions. Pascal's principle. Pascal's principle. His principle is the principle upon which devices are based that use confined liquid to multiply force. I see one of these in a mechanic shop. Hydraulic device, where they use that confined liquid, or the brakes in your car, hydraulic brakes. Important to remember that. We had another principle, another scientist said that when an object is submerged in a liquid, the weight of liquid it displaces is equal to the upward force lifting the object. Do you remember who that scientist was? Archimedes. And because it's true that an object submerged in a liquid displaces its weight of liquid, and the buoyant force acting upward equals the weight of displaced liquid, what determines whether or not an object floats? Density. Density determines whether or not an object will float. Liquid's resistance to flow. Viscosity, like the rather old honey in the honey jar. Viscosity. If liquid is flowing through a channel and the channel narrows, what will happen to the rate of liquid flow? It will speed up because the rate of flow stays constant. So as it narrows, it speeds up. And that was what I was looking for. I phrased the question poorly there. What do we call the absence of, as we move into chapter 4, the absence of air or other matter? Vacuum. Vacuum. You saw the little cartoons up in my classroom. One of my favorites is, hey, Uncle, I got a problem. Yeah, what is it? Well, it sort of borders on physics. It says if you're talking in a vacuum, would you still be heard? That's a tough one. Is the vacuum on or off? Anyway, that's great. Anyway, atmospheric pressure, again, pressing all over. You just don't feel it, right? I'm lifting, but there's also air lifting up under my hands as well. So we don't necessarily think about it. Archimedes' principle still applies. Remember, if you have something that is less dense than the air around you, helium, the ever flammable hydrogen, hot air, things like that, those things can rise. And we also talked about Bernoulli's principle. Bernoulli's principle said that if the speed of the air or the fluid increases, what will decrease? remember, I had a piece of paper or maybe a roll of toilet paper, blow the air over it. As the air speeds up, what decreases? It's pressure, it's lateral pressure. So as you blow air this way, the pressure this way decreases, which allows other pressure to lift and things like that. What do we call the device used to measure atmospheric pressure? Barometer. Who's credited with inventing it? Torricelli. And remember, we name units of atmospheric pressure after him. Remember, he used mercury in a tube and found that atmospheric pressure supports how many millimeters of mercury? 760. We call them torr. Every millimeter of mercury is a torr. So 760 torr is standard atmospheric pressure, also 1 atm. I don't believe you have to remember 1.013 E5 pascals. I don't think that's necessary for the final. A couple of gas laws. Remember, the one guy said if you increase the pressure on a gas, what happens to its volume? It decreases. Or, as you decrease the volume of a gas, what happens to its internal pressure? Increases. Pressure and volume, whether you're looking externally or internally, inversely related. What happens to the volume of a gas if you heat the gas? It expands, so it gets greater, it increases. And if you decrease temperature, volume in kind decreases. So that was Charles's law. Boyle's law was volume and pressure. Charles's law was pressure and temperature. A device that transports air or is driven by air pressure. Second would be an example of one. Pneumatic device. Hydraulic device uses confined liquid. Pneumatic device uses air. Like air brakes would use air. The only state of matter that has a definite shape. Solid. And we say definite, but if you apply enough force, you can mess up a solid as well, can't you? And so we still call that deformation. In general, those solids have to maintain their shape, right? So we call that property of a solid to keep its shape. Elasticity in general, two aspects to elasticity. If something resists deformation, it's said to be rigid, rigidity. And then if something allows for deformation but then recovers its shape, we say that's resilience. When something is deformed, if we take the amount of deformation compared to the original size, we call this relative deformation. What is that term that describes relative deformation?
Stress.
The other one. Strain. Strain is relative deformation. Stress is deformative pressure, deformative force per unit area. Something that doesn't really deform, it just sort of breaks or shatters. Your mother's priceless vase, handed down from generation to generation, and you busted it. Brittle. If only it weren't so brittle, it wouldn't have busted. Anyway, that's all for chapter 5. We're into chapter 6, speed in a particular direction. In general, any quantity that has magnitude and direction, or direction and magnitude, oh yeah. Vector, anything that has magnitude but not direction. Kendall must be tired. Class, anything that has magnitude, no direction. Not Gru. He is directionless, one could argue, but as far as for the testing purposes. Scalar. A scalar has no directional aspect to it. How do we find velocity? Kendall's running, and we, from point A to point B, we want to figure how fast she went. What do we do? That's instantaneous velocity is the first derivative. We talked about it in pre-calculus. Displacement over time. Displacement over time is velocity. However, if velocity changes, change in velocity per unit time is called acceleration. Second derivative. All right, change in velocity per unit time is acceleration. Negative acceleration is deceleration. Slowing down would be negative acceleration. For an object in free fall, we will assume its acceleration to be what? 9.80 meters per second squared, represented by the letter G. In reality, does an object really accelerate at that rate through our atmosphere? No. There is air resistance. And of course, you can increase air resistance by making yourself bigger, right? We said a fat person has a better chance of surviving a well, not really, but it's negligible difference. But a parachute would help, right? Increasing surface area while not necessarily increasing your mass. We said an object will continue falling and getting faster and faster and faster until eventually air resistance stops the object not from falling, but from accelerating. They'll continue to fall at whatever constant velocity. What's that fastest velocity at which a falling object can attain due to air resistance? Terminal velocity. Terminal velocity. We can think of falling object as, anyway, speaking of terminal. All right, let's see. We said if we got lots of vectors and they act at the same time on an object, we call them concurrent vectors. What we did with our vectors was we found one single vector that showed the outcome of all the other stuff. What do we call that one vector that shows the outcome of all the other concurrent vectors? The resultant vector. Resultant vector. We said if the vectors were collinear, we would either add them if they worked together or subtract them if they worked against each other. But if they acted at right angles to each other, we had to use what to find the resultant? Pythagorean theorem. And then we would use the arctangent to find the direction. We had law of sines and cosines. You don't need to know that for this exam. Pre-calculus exam, that's different, except you two are both exempt from it anyway. But if you weren't exempt from the pre-cal exam, you would need to know the laws of sines and cosines. We don't need to know that for here, because what we did was we took weird vectors, skewed vectors, and we said, well, this vector is a little bit up and a little bit forward. We made them into perpendicular vectors anyway. You won't have to do that because that's first semester math. That won't be on this exam. Anything launched or hurled through space is called? Projectile. The path of a projectile is referred to as its trajectory. And we said that a projectile, if there were no air resistance, would always travel in what path, what shape? A parabolic curve, a parabolic trajectory. We're in chapter 8. There was a guy who had 3 laws of motion. What was his name? Sir Isaac Newton. First law of motion. In a word? Inertia. Basically, an object tends to move at the same velocity unless some force comes in and intervenes. Okay, so what that means is that if a force intervenes, it's going to change the velocity. What do we call a change of velocity? So therefore, Newton said an outside force will cause acceleration. Second law of motion was an equation that showed how force can cause acceleration. F equals ma is the second law of motion. And let's see, we said for his third law, this was the fun one. For every force that acts on an object, there could be an equal and opposite reaction force, right? Your foot slides backward, it propels your body forward. You push down on the ground, it pushes your body up. You pull down on a rope, it pulls your body up. All those great mind equals blown moments, you know, your pull downs. You pull down on the bar, it pulls your body up. We call them pull-ups, but you're really pulling down. Anyway, you remember all that. As an object slides across a surface or goes through a medium, there is a resistive force that arises. Friction. And as Michael was noticing, slide lightly, little friction. Slide harder, more friction. The harder you push down, the harder it pushes up. What do we call the upward force exerted by a supporting surface? It is perpendicular, so we call it normal force. Normal force is that upward force. And so as I increase my force down on the surface, it increases its force up. That's more normal force. More normal force equals more friction force. Remember, there's really only 2 things friction depends upon: the normal force and the types of surfaces rubbing up against each other. The resistance to start something sliding is called static friction. Once something's moving, the friction that must be overcome to keep it moving was called kinetic friction. Talked about 4 fundamental forces in nature. What was the strongest of all the fundamental forces? No. Strong force. Strong force, remember, is what they believe held the nucleus together in an atom. The weakest of all the fundamental forces? Not weak force, gravitational force. Remember, gravitational force is always attractive, but it's very weakly attractive, any 2 masses. We also had electromagnetic force, which we talked about later, could be attractive or repulsive, depending on whether you have like charges or opposite charges, or like poles or opposite poles, which we did not get into with magnets, but you should remember from earlier science classes. And the weak force we thought maybe explains radioactive decay. For gravitational force, it helps to explain why our planets go around the sun, and it does go around the sun. We call this the heliocentric model. Remember, the Earth is at the center of it all. We said a guy came up with 3 laws not of motion, but of planetary motion. Newton was 3 laws of motion. Who was planetary motion guy? Not Galileo. Kepler, Johann Kepler. And his first law of planetary motion says that the planets go around the sun in what shape? Ellipses, which means there are points where the planets are closer to the sun and there are points where they will be further from the sun. When the planet gets closer to the sun, what happens? Burns up. No, it doesn't burn up. It speeds up when it gets closer to the sun. When it gets further from the sun, it slows down. Gravity, remember, is the pull of some celestial body on an object. Gravitational force is just any 2 masses. What do we call force that's transmitted through a string, rope, or other connector? Tension force, or tensile force, I suppose. When we take tension force. So much for chapter 9. Chapter 10. We talked about motion that repeats itself after the same lapse of time. It could be. That's a little too specific. Also, even more specific. Periodic motion repeats itself after the same lapse of time. There's a time period, so to speak, for the motion. Periodic motion repeats itself after the same lapse of time. Now, we did work with oscillatory motion, but oscillatory motion is more specific. It repeats itself after the same lapse of time, but oscillatory motion, the motion has to follow not just the same amount of time, but also the same pathway, like the masses going up and down on a spring or back and forth on a pendulum. In the latter 2 cases, there is a restorative force that pulls on it, right, with the spring or even the string pulling it back. So that's also called simple harmonic motion. We also have motion that goes around in a circle in the same circular path after the same lapse of time. So it's going at a constant speed. This is called, specifically, uniform circular motion. For an object in uniform circular motion, it's going in a constant circular path at a constant speed, but not a constant velocity. Because if it's going in a circle, it's constantly changing its direction. So we said that an object in a uniform circular motion is always accelerating. In which direction? Towards the center. Do we remember what we call the center-seeking acceleration? The other one. Centripetal. Make sure you know that term. Centripetal acceleration. Acceleration toward the center of the circular path. The reaction force, the center fleeing force, is the centrifugal force. Centripetal force pulls inward. And remember, we said centripetal force could be a tension force, it could be a friction force, it could even be a weight component. If you have a banked roadway, we said a component of weight could pull inward. It could be a gravitational force. In the case of, planetary motion, that's not technically circular, but we said that as an object hangs from a spring, weight pulls down. What's the force that pulls up? It's like tension, but we don't call it tension. It's not actually a string, it's a coil. Restorative force. Weight down, restorative force upward. And it's those 2 conflicting forces that produce the oscillation. Michael's like, gee, I'm glad I'm not taking this thing. I will say there is an element to which when you know you're exempt from something, you're like, your brain starts to check out a little bit. Your brain starts to unload that information or file it in the archives. I'm not upset at all because I know it's natural. I think I told you my physics teacher got frustrated with me after I found out I was going to be valedictorian, and suddenly my brain went to mush. She's like, I'm going to tell him to revoke that valedictorian status. It wasn't that I was trying to be a jerk about it, it's just my brain was like, oh, I got it now. Okay, set that information aside. Let me focus on my next steps, and it's just a natural thing. For an object that's oscillating, now that I made your classmates hate you. All right, for an object that's oscillating on a spring, there's 2 things that affect how rapidly it oscillates. So, first is okay, with the sound effects. What are the 2 things that affect oscillation, period? I'll take the thickness of the spring. The spring constant affects it, the strength of the spring, so to speak, which, as again, is affected by the thickness. And what was the other thing? The mass. How much mass you put on there, weight, you could say, assuming we're on planet Earth where gravity is relatively constant. But yeah, the mass and the spring constant. What about on a pendulum? What affects how long it takes for the pendulum to go back and forth? There's really one main thing. Well, no, because even if it went back a little ways, it would still take the same time as going back a big ways. It would just move slower, but it would still take the same time. The length. Now, technically, gravity is acceleration, but again, here on planet Earth, that's relatively constant. Most of us aren't going to the moon. So, practically speaking, the length is the main thing that affects how long a pendulum will take to go back and forth. Transfer of energy from one body to another, as evidenced by motion, is called transfer of energy from one body to another. I'm moving this water bottle. The water bottle has energy, but it's all my doing. Work. Work is a transfer of energy. Well, work, so if you cause something to move, you have done work. If nothing moves, no work. Work is measured in joules. Joules. Your husband doesn't buy any joules, ladies? Apparently he's not doing any work. Good for nothing, Bob. Well, anyway, don't talk to my wife about that. All right, let's see. However, the time rate of doing work, how much time it takes to do certain work, that's called power. Power is measured in watts. I love my wife, watts and watts. That is powerful love. We talked about simple machines. There were 6 of them. You're not going to be asked to list them, but you should know that a simple machine that basically has a long, inflexible rod that can be used to pry or lift, that's called a lever. And the pivot point of a lever is called the fulcrum. The object the lever is intended to move is called the load. So know some of those terms there. Talked about the inclined plane, that's a ramp. The screw, do you remember what we call the distance between the ridges of a screw? The pitch. Remember, the smaller the pitch, the greater the mechanical advantage could be for you. You also don't get it to lift very high or go in very fast or up and down very fast, but you get a lot of mechanical advantage. A circular pulley that's used to, circular lever that's used to redirect force is called a pulley. What if you use multiple pulleys at the same time, all together? Block and tackle. Block and tackle. We're in chapter 12. We're almost done with the first semester. The ability to do work. Kendall's like, I don't have any of this right now. I can't even move my pencil, Mr. Dudesky. Energy. Energy, the ability to do work. If work is a transfer of energy, energy is the ability to do work. Energy of motion. Kinetic energy. Energy an object acquires when it is exposed to a force. Potential energy, right? The water bottle suddenly is exposed to this gravitational force. Here, it was already on its supporting surface. It really couldn't go anywhere. When I get it out to the edge, it's exposed to the force. Just the slightest little bump, and gravity has the ability to act on it. I pull, a little paper dart, little hornet, whatever you call it, back on the rubber band. It's not moving, but there's potential. There's a force there just waiting to act, right? Let it fly. So potential energy. If an object is in motion, it's the product of its mass and its velocity is called its momentum. Mass and velocity is momentum. That's the end of the first semester. Let's go into the second semester. This is where we'll begin to hit more of these. So I reviewed a slew of terms from first semester. Not that many of them are actually going to appear on the exam. Now let's get to stuff that's going to show up a little bit more. As an object spins upon an axis, a spinning motion is referred to as rotary motion. If an object is going around in a circle, that's circular motion. But a spinning object has rotary motion. How fast an object spins is referred to as its, think of it as its rotational speed. But we call it not rotational speed, but angular velocity. Angular velocity, it's spin rate. For those who are baseball fans, which I'm beginning to be a little bit bigger of a baseball fan now that my Cardinals finally won some games. 2 out of 3 against the Cubs at Wrigley, swept the Red Sox at Fenway. Audrey doesn't like it. Hey, I'm as shocked as you are. and you're cursing your closer right about now for the first 2 games. He had nothing to do with the last game on Sunday night, which I did not watch. I did watch the other 2 games, and as MLB TV was giving free games of a day, so we got to watch those. But yeah, it was one of those. Got down to the end and like, oh, come on, Cardinals. And Kenley Jansen didn't come through for the Bo Sox, so go Cardinals. Anyway, starting to go. But anyway, when they talk about pitches, they talk about the spin rate. That's angular velocity. Spin rate can change. Spin rate can speed up or slow down, right? You think about the merry-go-round. It starts to slow down, so somebody comes along and gives it a push, and it spins faster again. We call this... Oh, the push is called torque. That was actually going to be my next question. The push itself has to have a certain component of force perpendicular to the radius. That's called torque. But the speed up of the spin rate is called angular acceleration. So a change in angular velocity is angular acceleration, and it's caused by torque. Torque is that perpendicular force perpendicular to the radius, that is. However, a body tends to maintain its rotary motion. When an object is spinning, it tends to just keep spinning at the same rate. If you wanted to stop it, you'd have to apply some torque. If you wanted to speed it up, you'd have to apply some torque. If an object's just sitting there and you want it to spin, you have to apply some torque because an object tends to maintain its rotary motion. What's this called? Sounds a lot like inertia, doesn't it? An object tends to maintain its velocity. Well, it's called rotational inertia. Tends to maintain its rotary motion. 2 factors affect rotational inertia. The mass of the object. We talked about putting Michael in the spinny chair versus Kendall in the spinny chair. Distribution of the mass. If Michael is all curled up in the fetal position, it's just, anyway, then his distribution of mass is relatively small, so it would be a little easier to spin him, whereas if you just like stretch out his arms and his legs as he sits in the chair, it's going to be a little bit harder to get him to be spinning there. We already asked torque. I was just a little ahead of things there. Chapter 14. We said thermal energy. Thermal energy refers to the actual atoms and molecules in an object, how much movement they have. More movement, more thermal energy. The measure of this thermal energy is called the object's temperature. Temperature. Now, how you measure temperature is you allow some of that thermal energy to flow into a thermometer. The flow of thermal energy is called heat. Okay, so heat's the flow of thermal energy. We said when we measure temperature or thermal energy, we measure it either Celsius, Fahrenheit, or Kelvin. But which one is it used in science anymore? Fahrenheit. Celsius, Kelvin are. The lowest obtainable temperature is believed to be, or well, has to be, absolute 0, which would be what on the Kelvin scale? On the Kelvin scale, 0 Kelvin. That's the easy one. Now for the harder one, which Michael was all gung-ho about, the Celsius scale. Negative 273.15 Celsius. And Fahrenheit would be around negative 458. If you heat an object, its atoms and molecules will move more. You add thermal energy, they move more. And as they move more, what happens to the object? It gets bigger, it expands. We call this thermal expansion. Thermal expansion depends on a few different factors. The most obvious is what I just referenced. As you add heat, as you change the temperature. So a temperature change, of course, affects thermal expansion. We also said that the original size or length, if we're talking about the length of the object, the size of the object matters. Something that's already bigger has the ability to expand more. And then the final factor, type of material matters. We said heat is actually measured in units like joules and BTUs and calories, things of that nature. No math on that. We said that if you want to evaporate a substance, you have to add a certain amount of heat for every gram of that substance, but it's not going to change the temperature any. It's just going to evaporate it. We call it this latent heat of vaporization. And in order to melt something, you would add latent heat of fusion. 3 ways heat can be transferred. One is you can touch it. Heat flows. Conduction. The other is that the heat is carried on fluid moving fluid currents. Convection. Or a really high energy body can actually heat even through a vacuum. Not toes.
Radiation.
Radiation, radioactive toes. No, radiation. Flow of energy through an elastic medium is seen visually as a wave. Talk about transverse waves. Remember, that's wave is moving perpendicular to the direction of the particles, and then longitudinal wave. It's parallel to wave direction. The high point of a longitudinal wave, low point when the waves bunch up on a longitudinal wave, compression, and when they spread out, rarefaction. Rarefaction. The distance from one compression to the next, or from one crest to the next. Wavelength. The amount of bunched up, and if it's okay, versus or if it's up and down versus up and down, up and down. The amount of displacement from equilibrium is called amplitude. If a wave strikes a surface and bounces off, we call this reflection. If a wave goes into a new medium and changes direction as a result, refraction. If a wave, as a 2 or 3 dimensional wave, passes through a narrow opening, spreads outward, we call this diffraction. If waves collide and so they cause new wave motion as a result of colliding, we call this superposition or interference. Interference if they're coming from opposite directions. I phrased it poorly. Superposition or interference. If a 2 or 3 dimensional wave is in a medium and the source of the wave or the observer of the wave is in motion, the wavelength or frequency, really both, wavelength and frequency, will appear to change. What do we call this change in wavelength and frequency of a 2 or 3 dimensional wave? Due to the motion of source or observer. Doppler effect. We think of it in sound waves, is pretty much what we look at. Doppler effect. The strength of a sound wave. Intensity. How do we perceive intensity? Loudness. The frequency of a sound wave is perceived as pitch. What do we measure loudness in, by the way? I forgot to ask. Decibels. Decibels. Had a lot of theories of light. The one that matters, though, is what we believe today, and it is that light travels both as a wave and as streams of particles. What do we call the particles, or packets of energy? Photons. And what type of wave is it? What type of wave is a light wave? It's part of a bigger group of waves. Electromagnetic wave. Remember, there are other electromagnetic waves as well. When we see light, we see colors. The colors we see are really just our eyes' way of perceiving different frequencies of light. So frequency of sound is pitch, frequency of light is color. 3 primary colors of light. Red, blue, green. If a material, like water, allows light to go right through it. Transparent. If, like milk, you can shine light through milk, but the light is scattered as it goes through because it's a colloid. That material that scatters light as it goes through. Translucent. If light doesn't go through, it either is absorbed or it reflects or a little of both, which is really what happens. Opaque. Primary subtractive pigments. Subtractive primary pigments are? Which are the colors you get in a printer. That brings us to 4th quarter material, the most recent material. Waves, light waves reflecting. We said when light strikes a surface, some of the light reflects. The ratio of reflected light to total light? Reflectance. If you can look in a surface and you see a clear reflection because of a smooth surface, we call this? Smooth surface produces clear image. Specular reflection. Uneven surface, even like a sheet of paper, it feels pretty smooth, but it's uneven, so that light rays are reflected in different directions. No clear image produced. Diffuse reflection. Law of reflection. Angle of incidence. For a mirror, if an image appears to form behind a mirror, real. If it reflects off the mirror and forms in front of the mirror, behind the mirror is virtual. If it reflects off a mirror and forms in front of a mirror, that's real image. If the spherical mirror appears to curve away from you, concave, the reflecting surface is on the inside of the curve, versus if it bulges out towards you, that's convex, where the reflecting surface is on the outside of the curve. What type of mirror has a perfect focal point?
Parabolic.
A parabolic mirror has a perfect focal point. We will do a little bit of math with that tomorrow. We are almost out of time. We got out of chapel just a couple minutes late. It's hurting me right now. For a transparent material, we said light goes through it, right? But transparent materials will slow down light a little as they go through. Transparent materials' resistance to transmission of light rays is called optical density. Optical density. And we can quantify optical density by comparing the speed of light in a vacuum to the speed of light in a medium. We call that refractive index. Refractive index. All right, we're going to have to do just a little bit of terms review tomorrow as well. Let me jot a note down that we got as far as refractive index. Tomorrow we'll finish up the terms, we'll go through the math. Wednesday, we'll have a short review before the exam. We'll kind of go over some more last things, anything we didn't cover, anything we need to cover some more. And then Wednesday after that last review is our exam. Have a wonderful rest of your day, and you are dismissed.